This video is to cover what we've gone over in Lesson 15. And Lesson 15 is just a continuation of Lesson 14, where we were writing equivalent expressions. The difference between this lesson and the last lesson is that now we are focusing on creating those expressions more than just verifying that expressions are equivalent. You can see that it says you've learned how different expressions can represent the same situation. And we want to take a look at the following problem. This swimming pool was designed so that sections of the pool can be used for different activities. The dimensions are given in meters. We want to write 3 different expressions to represent the total surface area of the pool. You can see where the pool is broken up into 4 different sections. You have a section for lap swimmers, a section for swim lessons, and a section for water therapy and the kids area. So these are the 4 different sections, and we want to cover the overall total area of the entire pool. In the Explore It section, we'll answer some questions to help see what is going on with this problem. We are told that you can think about the total surface area of the pool as the sum of the surface areas of the swimming sections and the other sections. And we want to write an expression that represents this way of thinking about the total surface area. So we want to think about area being length times width. And for the swimming section, the length is 25 and the width is 8 plus x. So that area is 25 times 8 plus x. And the area of the other sections has a length of x and a width of 8 plus x. So we can write that as x times 8 plus x. And because it's the area of the swimmer sections plus the area of the other sections, we would add these 2 together. The next bullet says you can think about the total surface area as 25 times 8 plus 8 times x plus 25 times x plus x squared. We want to draw and label a picture that shows this way of thinking about the total surface area. So we have 4 sections in our pool. We don't have our pool in front of us right now, but it was broken up into 4 sections for swim lessons, for swim lessons, for the lap swimmers, for water therapy, and for the kids. And in each of those sections we had measurements from here to here was 25, from here to here was x, from here to here was x, and from here to here was 8. So the 25 times 8 that we see would be the lap section. So we have a rectangle that has a length of 25 and a width of 8 for laps. Our 8x would be our water therapy, where the length is x and the width is 8. So we would have a smaller picture here. Our 25x would be our swim lessons area, where we have 25 as our length and x as our width. And our x squared would be our kids area, where we have a length of x and a width of x. These would be the 4 pictures that we could draw to represent this way of thinking. Our next bullet says you can think about the total surface area as 25 plus x times 8 plus x, and we want to explain the thinking behind this expression. If you think about the total area would be the combined length times the combined width. And when we combine those, for the length, we would have 25 plus x, and for the width, we would have 8 plus x. Therefore, this way of thinking about it is multiplying the total length by the total width. And this is what we've called in the classroom as a product of 2 sides. So in the 3 bullets, you've looked at one swimming pool broken down into 2 sections and then combined, one swimming pool broken down into 4 sections and then combined, and one swimming pool looked as a whole to get the area. If we want to find out more about this, it says the expressions you wrote to represent the surface area of the pool are equivalent expressions, which is what our lesson is about. Each expression shows a different way of looking at the situation. You can use the properties of operations to show that expressions are equivalent. Another way to test whether 2 or more expressions are equivalent is to evaluate them or substitute in a number for specific values of the variable. For example, you could evaluate each expression for x equals 10, and we're looking for all expressions to simplify to the same number when we are evaluating. You'll notice that when we evaluate these expressions for 10, everywhere we see x, we replace it with 10, and when we simplify, we get a value of 630. In each expression, we do this. So in the second, we replace our x's with 10s, carry out the operations, and when we simplify, we come up with 630. In the last, we replace our x's with 10s, and then we simplify to come up with 630. No matter which expression you use to find the total surface area of the pool, you will get 630 square meters as your answer. The 3 expressions are equivalent because of this. If you choose a different value for x, the 3 expressions will have a different value, but they will still be equivalent. We want to read the problem below and then explore different ways to write an expression to solve the problem. It states a group of rectangular community gardens is being built on an empty city block. The length of each garden will be 90 feet, but the widths of the gardens will vary. Let G stand for the widths of the garden. Think about different ways to find the perimeter of each garden. Then write an expression to represent the different ways. We have to pay attention here that we are no longer looking for area, and now we are looking for perimeter. You can see that they've drawn a picture. It definitely helps to draw a picture in most scenarios with a word problem. You could think about walking around the rectangle since we're talking about perimeter, and we're going to look for the sum of each of its sides. So its widths are G, and its lengths are 90 feet. And they have represented that here in this picture with 90 and 90, G and G. So to find the perimeter, you add all of the sides together. 90 plus G plus 90 plus G. Here again, wording is going to be important, so it's definitely a good thing to identify keywords. It says you can think about the perimeter of the rectangle as the sum of twice its length and twice its width. So if you see the perimeter as a sum of two equal lengths and two equal widths, you can multiply the length by 2 and the width by 2, and then add their products. So you have two 90s, which is 2 times 90, and two G's, which is 2 times G. And then add them together and you will have covered all 4 sides to get the perimeter. Now let's make some connections about what we did with this picture. Now you will write the perimeter in a third way and show that all expressions are equivalent. Number 2 says to look at the diagram on the previous page. I've drawn it in the corner for us. Find the lengths of 2 adjacent sides and write an expression for the sum of 2 adjacent sides. If we're looking for the sum of 2 adjacent sides, we're talking about 2 sides that are next to each other. So 90 and G. The sum of the 2 adjacent sides would look like 90 plus G. In 3, it says the other pair of adjacent sides have the same sum. Explain how you could think of the perimeter of the rectangular garden as a product of the sum of 2 sides. Well, if the sum of 2 sides is the same in both corners, then you could multiply the sum of 2 sides by 2 to cover all 4 sides. In number 4, we're told to write an expression for the perimeter of a rectangular garden as a product of the sum of 2 sides. So product means multiply. The sum of 2 sides here is 90 plus G. So we are multiplying 2 times 90 plus G. Now we want to use all 3 ways to show how to find the perimeter of a rectangular garden that is 16 feet long and 9 feet wide. So if we have a rectangular garden that is 16 feet long and 9 feet wide, and we're using all 3 ways, the first was that we could add everything together. 16 plus 9 plus 16 plus 9. The second was that we could say 2 times our length plus 2 times our width. And the third was that we could look at a product of the sum of 2 sides. So 2 times 16 plus 9. In order to prove that all of these are equivalent, we would carry out the operations. 16 plus 9 is 25, and 25 plus 16 is 41, and 41 plus 9 is 50. In our second, 2 times 16 is 32. And 2 times 9 is 18. And when you add 32 and 18, you come up with 50. In our final expression, we would do 16 plus 9 first, which we found was 25. And then you would multiply it by 2, giving you 50. Because they all reduce down to 50, we have proven that these are all equivalent. Number 6 says, does it matter which expression you use to find the perimeter? And the answer is no. It's your personal preference, because all of the expressions will give you the same answer if they are equivalent. We're going to go ahead and skip to part 3 on the modeled instruction. It says, read the problem below, then explore how to write different expressions to represent and solve it. The original price of a backpack is $40.90. The sale price is 30% off. Write 2 different expressions to represent the sale price. This should look familiar from what we've done in the past with tax, markup, and discount. And the fact that it's asking you to write 2 different expressions to represent the sale price means that you should probably think about method 1 and method 2 that we used for finding answers to these types of problems. We have a picture here in front of us called a bar diagram. And it says that you can draw a bar diagram to represent the situation. The whole bar represents the price of the backpack, which is $40.90. The shaded section represents the 30% discount, meaning the unshaded portion would be the portion that you would pay. In Model It, it says that you can calculate the sale price by subtracting the 30% discount from the original price. So that would be the sale price is equivalent to the original price minus the discount. And the discount was 30% of the original price. So you would take the original price, which is $40.90, and you would subtract 30% of the original price, which we know would be 0.3 times $40.90. This should look familiar from method 1. Below that, you can calculate the sale price by finding 70% of the original price. That's our method 2, where we figure out the percentage that the customer will actually pay. And if you are getting to take off 30%, then you can see that the customer is going to pay 70% of the price. So the sale price would be 70% of the original, which would be 0.7 times 40.90. This is method 2. If we want to explain how you could find the sale price of the backpack using 2 operations, that would be with method 1, where you would multiply the percent of the discount by the price, and then subtract it, and then subtract the product from the original. If we want to calculate the sale price of the backpack using 2 operations and show our work, we would take $40.90 and multiply it by 30%. And $40.90 times 30% is $12.27. and we would subtract that from the original, which was $40.90. Which gives us a price of $28.63 for the cost of this backpack. If we want to explain how you could find the sale price of the backpack using one operation, that would be method 2, where you multiply the percent you pay by the original. The next problem says calculate the sale price of the backpack using one operation and show your work. So the original price is $40.90, and if we are not paying 30%, then we are paying 70%. So you would multiply by 70%. And $40.90 times 70% is $28.63. Notice that the prices we came up with as final answers match, regardless of the method we used. So we know we have done our work correctly. In 13, it says, suppose the price of the backpack was P dollars. Write 2 different expressions to represent the sale price. So if we did not know what the price was, or if the price was something different, you would do the same thing, only replacing the amount with P. So we could take the price and subtract 30% of the price, or instead we could simply pay 70% of the price. Now let's try 2 different problems related to what we just did. Use what you just learned to solve these problems and show your work. The price of a flash drive that regularly sells for $16 is increased by 15%. We want to write 2 different expressions to find the new price. Well, we would take the price of the flash drive and increase it by 15% of that price, which would be $16 plus 15% of $16. When we did that math and simplified, we would see that the new price is $18.40. Because when you multiply 15% of $16, you come up with $2.40. So the markup is $2.40. But we could go directly to the answer originally. When we say that the customer is not going to pay $16, the customer is now going to pay 115% of that price, because they're going to pay the original plus 15% more. Well, that looks like 1.15 times P, so 115% of the price, meaning we would do 1.15 times $16. And when you calculate that, you come up with $18.40. So we have a match, meaning that we have 2 equivalent expressions, and we've even gone so far as to prove it. The next problem states the original price of a DVD is represented by the variable X. If the DVD is discounted 45%, write a subtraction expression and a multiplication expression to represent its sales price. The directions were specific in what they were looking for. And discount is subtracted, so it would make sense that they were asking for a subtraction expression. If that's the case, then we have the cost of the DVD, which is X, and we are subtracting the discount, and the discount would be 45% of X, or 45% of the cost of that DVD, so 0.45X. That is our subtraction expression. With discount, according to method 2, we would say what percent the customer is actually going to pay. And if the customer is being discounted 45%, then they would pay 55% of that price, because 100% minus 45% is 55%. So the customer will pay 55% of the original cost of that DVD. Therefore, we now have two different expressions that reduce to the same thing, and we could prove it by simplifying the expressions or by evaluating. If we simplified the expressions, then our first expression, the coefficient here is 1, so we would have 1 minus 0.45, which would give us 0.55x, which is the same thing as what we had in method 2. So we do show that we have equivalent expressions here.